All right. Was everyone able to get the new script?
Yes.
All right, let's get moving then. We're gonna talk a little bit before we get the coding. So if you're still doing that, you're gonna have a little bit of time to catch up. All right, so go ahead and launch this script on your R project. So 14 satellite project. So last time we connected to the Copernicus European Space Agency API, and we retrieved all imagery for the growing season, but then we asked for on the server side, on the cloud side, for it to calculate the mean on a pixel basis for us. And then we just downloaded that mean pixel green NDVI across the growing season. This time, or on this exercise, I want to show you how would you actually download all those daily available images for this field rather than asking for and just downloading the mean. So this is what we're going to do is basically retrieve all the daily imagery available for that field for this year and then download all those daily images as well. So just a quick intro, we already talked about there are two ways that we can retrieve imagery. One is you can get all the images available for that field and that time period that we specify, or we can ask for a summary like the mean, like what we did last class. While the mean across the growing season can be very informative, right? It still gives us an idea of how different parts of the field on average responded when it was measured through green NDVI. So it still gives us a good idea of the overall behavior. However, it doesn't really let us understand the temporal time series, the development of the crop, and anything related to stress, different stresses occurring different timings. It doesn't allow us to learn that component of it. So when we download the daily imagery, we'll be able to really see those patterns and understand how the field as a whole is evolving over time. So on this script, we're gonna retrieve all of the daily available imagery for this field and download that imagery and then work on that. Do some maps, do some plots to understand the behavior of the of different parts of the field. And again, we do have 3 years of field data, so it would make sense that we would analyze all those 3 years of imagery as well. Today we're going to start off with just the 2017, just like we did last class. So last class we got the mean green NDVI for the 2017 growing season. This time we're going to get the daily imagery for this same year. A lot of the initial steps are still very similar to what we did for the mean. So, if you want to go ahead and load all the packages, I left you here the code that we already developed to bring in the boundary. If your path is a little bit different because of how you named your files, remember that you just need to specify this path to retrieve the boundary, which we did on the 05 digitizing project. Then we're transforming that to this CRS and doing a negative buffer, just like we did before. The reason for the negative buffer is if we do not do a negative buffer, it is common for pixels around and outside the border of the field to have a very low value of green NDVI. And so I just don't want to have that interference there when we do plots and things like that. So if you run, you get the field there. Just a very quick EDA, just to check that the field is actually where we would expect, and you can see that it is. It is our same old field as we've been working with. Now the next step is going to be for us to connect to the API, right? So we do that in a couple of different steps. First, we run this connection here. We need to just wait for that to finalize connecting to the service. So we just did it on my side. Once it is connected, we have to do the login just like before. So if you run the next chunk and then you check on your console, you have this prompt for you to click on enter or push the keyboard enter. If you do that, it's going to open a new window for us, asking us to log into the service. So just go ahead and log in using the credentials that you already uh, signed up in the past, and then you're gonna say yes to that. Do you grant these access privileges? Yes. Once you log in, you can just return to R. You're gonna see that on your console is gonna say login successful. So now we are connected to the server, we have access to it, and we can start our process. Just like last class, we are going to start the process here and assigning that to this object called P. It went through on my side. And now we need to determine some of the specifics of what we are retrieving. So we're going to use this function called load collection. This is exactly the same as last time. So we're using load collection here. We're pulling the Sentinel-2. So Sentinel-2 is the satellite, right? And then L2A is the product. If you remember from the previous class, L2A is the most processed product that we have access to. It is the surface reflectance, which is what we need in agriculture. Then we give a spatial extent of our field boundary. We give a temporal extent. So this is the year, month, and day of when we want the imagery to start and end. I'm just keeping that here between May 1st and November 30th. This is a cotton field. This is approximately the growing season of cotton here in Georgia. If you are working with other crops, perhaps corn, this window would be slightly different. Perhaps it would start in March and then only go until September. And then we're also saying what bands we want. So here we want band 3, 8, and the SCL. If you remember from the documentation of Sentinel-2 that we also saw last class, band 3 represents the green band, band 8 represents the near-infrared band, and both of these bands have a 10-meter spatial resolution. There are other bands for near-infrared that have other numbers, but they're all coarser. They're all either 20 or even 60 meter spatial resolution. These band 3 and 8 are at the finest spatial scale of 10 meters. And then the SCL we're using just to filter out cloud pixels. Go ahead and run it. I'm going to close this output here, but just to keep going. Once we retrieve the imagery of a specific collection, so Sentinel-2, of a specific prototype, for our spatial extent of the field, and for the temporal extent of the growing season, and just keeping the bands of interest, now we can use that band, specifically the SCL band, to only keep vegetation and non-vegetation in our image, and therefore filtering out other classes that include cloud or cirrus or shadow or things of that sort. So we first create that filter function that's going to do it for us. And then we apply the reduce dimension. So remember, this function here, reduce dimension, we've used that to reduce the dimension, in this case here, of the bands. We've also used to create the vegetation index in the future chunk, and also to reduce the temporal dimension of time, of days. In this case, we're just doing the cloud reduce to filter out the pixels that are not plants or that are cloud in that case. So run that, and then also remember to run the cloud reduced, which is something that I forgot to go through on the first time we did it last class. So make sure you run both of them. All right, so with this, we basically removed our cloud pixels. Now the next step is to create a vegetation index. So now we're going to reduce dimensions. It's going to be using the data coming in is that the one that we just removed clouds. The dimension we're reducing is bands, and then the reducer, which is the function that is going to be applied, is just setting up two bands, so B3 and B8 as their own objects, and then returning the result of this formula, which is the formula for green and DVI. So make sure you run the spectral reduce. And then that's pretty much it on the processing side. If you remember from the previous class, if you were to compare this script with that script, we on the previous script that we got the mean data, we would have here another chunk for the temporal reducer of getting the mean over time. In this case, since we are not taking the mean over time, we're just not going to apply the reducer. That is one of the differences between getting the mean over the growing season or getting all the images over the growing season. If you want all the images, you just do not reduce on the temporal scale. With that, we just come to compiling the results. So here, if you want to start coding with me, this is going to be a new code for you. We're going to give the assignment symbol. We give our process object, which is called P. And then we call the function save result, which is the same one that we used last time. Here, our data is going to be equal to the spectral reduce, the one that we created just above. And then our format is going to be the same as before, gtiff, like that. So we can go ahead and run it. One thing for you to remember is here, if you were to go back and compare this script with the previous one we had another step here for the temporal reducer, and then the data here would be the temporal reduce objects. In this case, we're not doing a temporal reducer, therefore we don't even have that object here, so we just input here the spectral reduce, which was the last reducer that we applied in this case of the daily data. All right, so now we are basically ready to start the process of downloading all those individual images from the server. One difference here is so before we're just asking for one image, right? It was just the mean. Now we're gonna have more than one. At this point, we don't know yet how many, but we're gonna have more than one for sure. With that, because we're asking for more than one image, there's a little bit of a difference in the process of retrieving this from the server. So one of the differences is that we're gonna have to create a job. So here on the job, give a assignment symbol. We're gonna use the function create underscore job. It has an argument for graph, which is basically this results int object. So it's the one that has all of our processing steps plus the format that we want it exported. Let's give it a title as well. So a title, I just want to say GNDVI. And then let's give a description too. So description, I just want to say growing season GNDVI. Now you can run this. Here, we're just creating the job. So the job was, to me, says job was successfully registered on the back end. So we created the job. So the server knows that, hey, this is what we want to do, but we have not asked yet for the job to start. We have not asked the server to start working on this job yet. So the next step is we're gonna do exactly that. So in this next chunk, there is a function called start underscore job that just has an argument called job that is going to be equal to our object of name job that we created above. So if you have this and you run it, this job is going to basically be finally starting to be processed on the cloud server side of things. So notice that all the processing, everything it's not being done in our computer. It's being done on the cloud. So once we start this job, the images are retrieved and they're processed according to all the reducer steps that we specified in the script, all happening on the server side. Only after the job has been finalized, we'll be able to download the images. So then a question that you may ask is, okay, so how do we know when the images are finally processed and ready for downloads? Well, it's kind of a manual process to some extent, but in the chunk below, we're going to do that. So if you come on this chunk here and you type the function list underscore jobs and you run it, you may have just one line. I have many already because I've been running this for a few times before this class. But we can see here that, at least on my side, the one on top is the job that we just submitted. We see it has a title, it has an ID, it has a status. For me, it's showing queued, so it is in line for being processed. And then we have a few more. Excuse me, I was gonna sneeze and stopped. We have a few more columns here for created, updated, and then cost, budget, and plan. In our case, we are not paying for this because we're using for research, so there is no cost or budget or plan. But if we were using a product that had a cost, then maybe we would see that information here. Now, how do we know then when this job has been finalized? Well, you just have to keep running this list jobs function. Now you see I just reran it, and on my side it's showing running. So it was previously showing queued. Now it is running on the server side. So it's actually going through retrieving the images, applying the reducers, and then processing them so we can download them. So basically at this level, we just have to run this list jobs until we see our running change to finished. Whenever it changes to finished, then at that point we'll be able to download. But before that happens, we're gonna have to wait. On my side, it's still running. I do want to make something here while we wait. And basically, we're just gonna have to wait a little bit. On my side, it was taking 3 to 4 minutes for it to be finished. Still running on my side. Is everyone able to see the running icon on your or board on your side? Okay, perfect. Yeah, we're just gonna wait a little bit here for that to go through. And then once it finishes running, then we'll be able to start downloading the images to our computer. All right,
Mr. Bartos, like for me, it's showing queued.
it's still showing queued.
Yes.
Have you run already again the chunk? Yeah, so you need to run the chunk again to see if there are any updates. It's not going to update by itself like the text. So for me, it's showing that's finished. Is anyone else not finished?
It's not finished for me, but it's running.
Yeah, running.
Okay. Well, I'm gonna wait a little longer here. Well, I think while it's running for you all, I do want to show you the next chunk because you may not be able to actually run the next chunk before it's finished, but at least you can copy the code and when it's finished, you can run on your side. But I can show you how it looks on my side. So on my side, this job has been finished. So we can check this job a little bit, see what's in it. There is a function called list underscore results. You can type this, just I don't think you're going to be able to run it before yours is finished. But if you just say job equals job, so we want to list the results of our job that we just submitted. Whenever your job is finished, this is what you're going to see. So it's basically a description of the job that you submitted to the server. So it shows you the spatial extent. If you keep going lower, well, going lower here on the output, so not on Quarto, but on the output here, it's going to show you a temporal extent. It's going to tell you the provider. So in this case is the processor was Vital. This is the backend of OpenEO that does the processing for us. And then it's going to show us the assets. No, the name of it. Okay. So assets here is showing us each image that was able to retrieve for us. So the first one here was 2017-0502 was the first image within our time period that we defined. We have a choice of downloading the GeoTIFF or copying the URL. You could do that by clicking here. We're not going to do that. We're going to use code, but just want to show you. So it shows us the bands. It has one band, which is just our green NDVI, and it's showing the maximum, mean, minimum, standard deviation, and value percent. It tells us a little bit about the projections of the bounding box dimensions and the EPSG code. If you keep scrolling, you're going to see more images. So each entry here is going to be a new image. So here, 2017-05-15, so May 15 of 2017, there was another image that we can just keep checking. And if you keep scrolling, there's going to be a lot of images here. This is all still on the server. It's not in our computer yet. Let me come back here. So this is just the server telling you what it did and what it has available for you to download if you wish, but we have not downloaded yet. So before I do move on to the download part, I just want to make sure everyone has a finished on their status. So if you rerun the chunk, you should see a finished. Let me ask differently. Is anyone not seeing finished on your status?
To me, it's shown an error, Dr. Bastos. Like it was running, started running, but after running, now showing an error in its status.
So what does it say?
It says just error in this status bar.
Hmm, interesting. Is anyone else having issues?
No. Oh,
Okay, so what is that Mohit?
Yes, Dr. Bastos.
So Mohit, I'm not sure what is going on. What I would suggest is try to start job again. So try starting job and then checking the list jobs function and see if it starts a new job for you. Um, I think that would be the solution that I would try. Um, because it takes a little moment, I think I'm gonna keep going here. What I would say is you can still copy the code related to the back to the API. You're just gonna have to wait to actually run it after you have a finished job. If you don't have a finished job, Neva, are you following the code as well?
Yes, I am.
Okay, were you able to
Yes,
or
my job is finished.
okay, so after we download the images here, Neva, if you could perhaps send the files to Mohit.
Yeah,
Just
sure.
all right,
I will do that.
thanks, Neva. So Mohit, in the meantime,
Hmm.
do
Dr.
try.
Bastos, now it's finished. It's finished.
Okay, great. So no worries, Neva. All right, sounds great. So everyone was able to finish the job. Now the next step is going to be to download those results. So on the next chunk here, type the download results function. So here we're gonna say what was the job name is just so the job argument, so we just say job because that's how we name our job. And then we're going to specify which folder we want the imagery to be saved. So I want to specify here // to get outside of code, go inside of output, And then because there's going to be a lot of images, I want to save them in a subfolder inside output called Sentinel, and then give a /. So this is what you should see on your download results. If you go ahead and run this function, it takes just a quick second or a quick moment here to go through. And once it goes through, you're going to see this output here of a lot of images or paths to a lot of images. You can just close this output window because it's really not that useful. But you can come on your Files tab, go to the Output folder, check your Sentinel subfolder. Here you have many images, all the images available for your field within the time frame that we specified. So we see that it's starting, so the time range that we gave was May 1st through November 30th, I believe. So you see here that the first image available was May 2nd, and then we had like 13 days in between that and the next one. So May 15 was the next one. Then May 16 we had another one, and so on. The last imagery that we had was actually November 26, within the time period that we specified. All right. So we just downloaded all those images to our computer. Imagine that, if you are working with imagery, I mean, you could be working with imagery for any of your trials at any time point. Sentinel imagery, I believe, is available, I want to say since 2017. I could be wrong. It could be a little bit earlier than that. But anyways, it just means that if you're joining, your program now, or if you're already working on your program, but you wish you had imagery for your fields that you already worked with, you can go back in time using Sentinel for free and downloading images for the field that you're currently working with. So that's a really powerful tool that we have free of cost. All right, so we actually have a total of 30 images for this field within that growing season. So let's go ahead now and import all those images, start processing them in R, and start making some plots for us to understand how gradient DVI evolved in this field in 2017. All right, so because we have 30 images here, we could do 30 read stars. So these are TIFF files. These are raster files, right? So because they're raster, we need to use stars. We could use 30 times read stars, but we're not going to do that, right? We're going to do on a little bit more automated style here. The first thing for that to work is we need to determine the path and the file names of all these files. I need to have the path to these files as a string in R, so we can import these files. So we're going to do that in this next chunk here called rest, or with this next object called rest list. So give the assignment symbol. We're going to use a function called list.files, where we're basically going to tell it to tell us all the files that are in a given folder and that follow a given pattern. That's pretty much what we're going to ask. So the first part here is called path. So the path is which folder I want this function to look at, to search for. This is going to be .. output Sentinel. That's the folder that we wanted to look for patterns. The next argument here is the actual pattern. So the pattern is going to be in quotation marks .tiff $. So this coding here is basically going to look in this path for any file that has an extension of .tiff. And it will return back to us the full path to that file, which is what we're going to use then to automatically import all of them using read stars. A few more things we need to do here is it has an argument for all .files. The default is false. We want to set it to true. And then it has an argument for full names. the default is false. I want to set it to true. If you run this and you print rest list, this is basically a list with all the path for each one of the file of the raster files that we brought from Sentinel. Now, if you imagine, now that we know the path to it, we can basically specify this path to read stars. But we're going to have to do that on an iterative way. And that's what we're going to do in the next chunk. If you come here on the next chunk, give it the assignment symbol. The first thing we need to do here is to create a data frame that we're then going to populate with these read stars functions and TIFF files. Sorry, I almost sneezed again, but it's canceling midway. Okay, so let's call the function data.frame. I want to create a column here called source, and under this column, I want to give the rest list objects. So if you just run this and you print all images W, this is what we have. It's just a data frame with 30 rows with one column where each cell here has the path and the file name associated with each one of the rasters that we do want to import. Something I want to do here that is not completely I mean, it is here, but it's not in the data set yet. I want to have a column here that tells me what was the date that each one of these flights or these images were collected. If you notice, the file name that we downloaded, they all have the dates in them, right? So this is the date for this TIFF file and so on. So that information is part of, well, it's part of the file name. And in our case, that file name is represented in the source column right there. Any thoughts on how can we retrieve that date and have another column that is called date that only has the date and not all the other text around? I don't remember if we used this function in this course already. Maybe not. So maybe that's why it's not coming to you. So let's go ahead and implement it. So give it the assignment symbol. Go on the next row. We're gonna do a mutate because I want to create a new column. I want to call that column date. And the way that we're going to basically sample, so this is a string, right? We want to sample this string, or not just sample, but we want to extract something from this string. So we're gonna use a function called str_sub. This is a function from the string_r package, which is that package that is so useful for handling strings in so many different ways. Do make sure you check their vignette so you get some ideas. So here we give the source column. That's the column we want to subset. So a string subset, that's what we're doing. The way that this function works is you need to give a position. So let's say if I want to extract starting on this position and ending on this position, you would basically have to count 1, 2, 3, 4, and so on until we figure out what position is the 2, what position is the 6. I did that myself already, so you're not going to have to do it. So the 2 is on the position 28 of that string. So that's where we want to start. And the 6 is on the position 37. Of course, I'm talking about this 2 and this 6 specifically, but doing this is going to work for all of them because it's just a position and because the pattern is the same, right? The pattern of all the files is the same. Position 28 will always be this 2. Position 37 will always be the last number of the date. So this is going to work well. If you run this and you print all images W, and you scroll to the right, now we have a column that says date, and we only have the dates. So we just did a subset of the string based on the position, because the position of the date was the same across all of the rows. And then next, I do want to transform. So right now, this date column is character. I do want to transform this to a type date in R. So we're going to use a mutate here. I'm going to overwrite on the same column name, so date again. We're going to use a function s.date with the uppercase D, where the first thing we give is which column we want to transform to date, and then we need to give a pattern. So the pattern we want to transform into is percent uppercase Y. This means uppercase Y means the full year in 4 digits, so 2022 or 2017 in this case, and not just 17. Then if we look at the date itself, it has a dash, so we give the dash here, still within the quotation marks. Then the month comes after, so the code for month is percent lowercase m. After the month, it has another dash, so we give the dash here. And then it has the day, and the code for day is percent lowercase d. So here we're basically specifying what is the current format of the date. So the sDate function understands what it is and transforms that to an actual date column. If you run this and you print it, now our date column is of type date. And you may be asking, well, why do we have to change from character to date? So what difference does that make? It makes a difference in some specific cases. For us, it's going to make a difference when we plot it, when we put this in ggplot. And you see when we get there. All right. So right now, this is how our...
Dr. Bastos, my dates are showing 0017 instead of 2017. I don't know what's wrong.
0017.
All of them.
Okay, so go back to rest list. Did you add this / here?
I did.
Okay, so when you see your rest list, do you see a similar pattern as I did here? Or do you see different?
Yeah, it is similar. Should I count the number of the 2837 if it is different for me?
I mean, you can play around with the number. So it is what is it showing to you? Like what is on the dates?
This says 0017-05-02. Just zeros in place of twos.
That is very odd. So when you look at the file name, does it have zeros on the file name?
No, the file names are the same as yours.
Anyone else having this issue?
I see the same thing.
Dr. Bastos, I think for some of us, maybe the number is 27 instead of 28, because I also got the same issue and I tried the number 27 and now it's showing 2017.
Okay, so maybe it may be a difference in how Windows so I'm working on a Mac.
Yes, maybe
Windows,
I'm in the
Windows
window.
maybe a difference of how they tell the path. Okay, so Mohit was saying that he tried changing to 27 instead. Kiathi, try that and see if you get...
Yeah. Yeah, it's good now.
Okay, awesome.
Thank you.
Yeah, if you had to go back, yeah, it may just be the way that these operating systems are creating the paths, but awesome. Thanks, Mohit, for the help. All right, on my case, I'm gonna leave 28 because if I don't, then it brings the underscore together. But yeah, make sure that you do in a way that works on your operating system. All right, so now we have this source. we have the date. So the date was just for us to extract this ID that works for us. Is we're not gonna really need the date to import all the TIFF files. But now, if you give a pipe and you come after the next comment, here's my vision for what I want to do. I want to have a column that's going to be called image, and each cell of that column is going to be a stars object for each one of those dates. We did a little bit of this when we worked with the creating many ANOVAs in the previous exercise, that we used the concept of the map function. Map in the sense of doing iteration. If you're taking my other course, you're probably more familiar with it by this point. That is not the goal of this course, to really fully understand that function. I just want you to be able to at least understand how it's working, but not to fully know how to use it, in a lot of depth. So let's call for a mutate. We're going to, the name of this next column is going to be image. So here we're going to be doing iteration, right? So we're going to iterate over 30 files, where we're basically going to be applying the function read stars to each one of those paths, and then saving that stars object as a cell under this image column. The way that it works is we call the function map, which again is not map in a geographical cartographic setup, is a map for iteration. We tell it what is the column that we want to iterate over. The column we want to iterate over is source. We want to take this path and read that and put that path into read stars, and reading that star file or that TIFF file as a stars object, and then do that 30 times. So the first thing here inside of the map is the name of the column, which is called source. Now you can break line, give it a tilde, and we're gonna call the function read underscore stars, just like we have used before. Here on the read stars, we change, or we specify what is the value we want to read in, which is .x. .x is just a placeholder for each row of the column source. And if you go back, the column source has our path. This is what the column source has. Before we run this, right after the read stars, give it a pipe, because as it imports the read stars, I already want to do an ST transform using the CRS equals to 6345. So we're importing and already changing the CRS right on the fly. If you run this and you print all images W, this is what you should see now. You should see a column called image, and each one of these cells is their individual stars object related to this date. All right. If we were to just pull the first stars object, so if we do all images, $image, and then just pull this first one here, it is basically a stars object, just like we're used to. So we basically just imported 30 stars objects by using this line of code. Pretty cool, right? All right, so now give it a pipe. I want to do a little bit of wrangling here. So the wrangling I want to do is I want to rename. So right now, all of the layers, the name of the variable that is stored in each one of these stars objects is the actual name of the file. I mean, it is green in DVI, but it is named as the name of the file, which is not helpful for us. So I want to change this name here to actually be the file name, or to actually be green in DVI instead of the file name. You know what? I was going to do that in another code, but we can actually just keep working here as we read. So let's just go ahead right after this ST transform, give it a pipe. We're going to use the function rename. and we're gonna say GNDVI equals 1. So we're basically saying the first position, the first data column in this stars object, we want to rename that to green NDVI. Let's just run that. Well, make sure you remove this pipe at the end so it doesn't try to keep running. Let's just run this and then print again image1 to see how that looks like. All right, so it has GNDVI right there. That's all good. That's all that we needed. Because so on my previous code, I was doing this on a separate mapping function that would come after here. Since I decided right now to just do that right on the first one, you can delete the wrangling each image comment. And let's just call this image as image W to mean that's been it's already been wrangled. Now we just go ahead and run it and print it. So we have our source, we have our date, and we have image W, which is those stars objects that we imported, changed the CRS, and renamed to green NDVI. Now the next thing is I want to have a column that helps us. I really don't care about this source anymore, but I do want to create a column that is image ID, just so we have another column to help us identify what image we're working with. So if you go back to the code, add a pipe, go after that, create an image ID comment. We're going to use mutate. I want to call this image ID, going to be equal to 1:in_row dot. So this basically calculates first the number of rows of this data frame, and then it just makes a sequence of numbers from 1 to that n row. So if you print it or run it and then print it, you're going to see that now we have an image ID as well. And then finally, I just want to select the variables and also change their order. So give it a pipe, go after the selecting variables. Let's do a dplyr select, where I first want to have image ID, then the date, and then the image_W as our objects. So if you run this and you print all images W, that's exactly what we have. Image ID, the date, and the stars object under the image W column. All right, any questions at this point? All right, I don't hear anything, so let's keep moving. Now, let's do a quick EDA. Let's take a quick visualization of one of the images. So let's call map view for that, for a fast map. We call here the object name, so all images _W. We need to use the $sign to get inside the image ID. And I want to get just one of those images, and I want to get the one on the 5th position. So that would be on July 1st. So let's just pull that on the 5th position and plot it. Ah, that is not what I was. Oh, not image ID. Sorry, image W, not image ID. Okay, there we go. So yeah, I first typed image ID. That's not what we wanted. We wanted image W, as that's the name of the column that has our image. So this is the green NDVI image for July 1st for this field. One thing that you notice is we have pixels that are outside of the field, right? So we got kind of like a type, like a information for the bounding box of the field. So one processing step I want to do next is just to crop this to the field only. So we remove the pixels from outside. We could also check other images here. So let's see if we check the first one. You know, I mean, these images are all different, obviously. They are for different dates, but we could have checked any of them. I checked number 5 because it was a clean one. Now check this out. So I just ran for image number 2, which is May 15. What is going on here? Any guesses?
Is that a cloud cover?
Yes, exactly. So this is cloud coverage or pixels that were classified as cloud that we removed as part of our steps when we were retrieving the imagery. So every time there is clouds over a field and a satellite comes through and has a multispectral sensor like this one, if the field is covered by clouds, you may actually miss the whole field, which is very common. And in fact, if you remember, the temporal resolution of Sentinel, the nominal temporal resolution is 5, but we can get a new image about every 2 to 4 days most of the time. If you check our dates, I mean, we have May 2nd, and then the next one is May 15. What happened here? Why do we have so many dates missing? That's basically because all those images that were collected in between these two dates were completely classified as clouds. So if every pixel is classified as cloud, we just don't get an image, right? It was completely cloud covered. Now, if when the satellite goes by, there is still some pixels that can be seen, but the rest of the field is covered by clouds, then it gives you those pixels, but it removes the ones that it classified as cloud. So you are sure that you're not using, wrong data. So that's basically why we have these gaps in this specific date, and also the reason why we don't have some dates altogether. And again, this is one limitation of satellites, right? So satellites with multispectral sensors are going to be susceptible to cloud coverage. So if you really need an image, and it's been cloudy, which here in Georgia is pretty common during the summertime, you may have to go out and fly a drone to make sure you get imagery because satellites are going to be impacted by the cloud coverage. All right, so the next step I want to do here is to crop those images to the field boundary that we have. So we're going to do that here on this next chunk. Give it the assignment symbol. We're going to start off with all images W object, which is where all those stars are. So imagine now that I want to basically I want to crop all 30 rasters or stars objects in this all images W object. So every time that you think, man, I have 30 items that I need to do something with them, and the something is the same across all of them, you should be thinking about iteration. Again, we're going to use here the map function to iterate the cropping tool across all of those stars objects. So starting with all images W, let's give it a pipe. Let's ask for a mutate to create a column called crop, meaning that it's going to be the cropped image. Because we're doing iteration, we need the map function. The first argument of the map function is which column we want to iterate over. Now that column, if I just print all images W, that column is called image W as well, right? That is where the stars objects are. So I want to iterate over image underscore W. Give it a comma. We're gonna give it a tilde and call for st crop is the name of the function, where the first argument is the stars object, that in this case, it is the iterating element. So we need to specify by the point X, which then is a placeholder for each row of image W column. And then we give here what is the SF object that we want to crop with, which is our object called field. If you run this, we get some warnings, but nothing to scare us off. If you print this object, now you have image ID, date, image W, and also crop. If we just show a map of one of those cropped stars. So maybe the fifth one again, as we checked above the fifth one before cropping, which looked like this. Now, if we check again the fifth one here, oops, here, we can check that that's been cropped. It has worked, right? And then, so right now our all images crop object has the image W column and the crop column. Really, we do not need image W anymore because we just cropped it, and that is what we're going to keep using. So we can just select out image W. So go back to the code. Let's do a dplyr select. Also, I only want to keep date and crop. That's all gonna need for now. So if you run that and you print it, you should now see just the date and the crop columns, where the date is a date object and the crop is the cropped stars object for each date of this field. All right. So the next step we want to do here on the processing is I basically want to transform all of these stars objects into SF. The reason for that is because I think it's going to be easier for us to understand some of the behaviors when we start plotting. And so that's what we're going to do in the next chunk. And then that's going to be the last chunk before we actually make some plots. So we're almost getting to the actual interesting part. This is all wrangling. As you are noticing, perhaps in this class and across any data science project related to precision ag or not, wrangling a lot of the times is what takes the most of your actual effort working on the project. And we can see that here. We've been wrangling things for about an hour now. All right, so the next part here is going to be to extract the pixel information. So here on this object, we're going to start off with the all images underscore crop, which is what we just created above, right? So where we have date and the cropped stars. Let's give it a pipe. I want to create a new column that's going to be called pixel. So mutate pixel. Let's give it the equal sign. Basically, what I want to do here is take each one of those stars and plug them into an ST as SF. That's what I'm doing for each one of them. Because we're doing the same thing over many times, in this case, over 30 times, we're going to use the map function again. So the column name that we want to basically use to transform from stars to SF is called crop. That's what goes here. Give it a comma, break line, give it a tilde. We want to use the function st underscore s underscore sf that you're all familiar with. The object that goes here is .x. That is a placeholder for each row under crop. So each time it does for one of them, .x is what is identifying which row is working on. And then still inside the STSF, I want to change an argument for s underscore points equals to false. I don't want it to give me points. I still want it to give me polygons. If you go ahead and run this, and you print this object pixels, now you have the date column, the crop column, and the pixel column. And you can see that the pixel column now is of type SF, whereas the crop is of type stars. Let's pull out this first pixel here, or pixel object here. So pixels, $, pixel, double bracket 1. Well, this pretty much looks like an SF object, right? We have gradient DVI, we have our geometry, we have 3,568 features on this field. Why do you think this number, why do you think we have this number? What does this represent?
Number of pixels.
Number of pixels, right? In this case, number of polygons, but that were pixels that now we transform into polygons. Yes, thanks, Polly. So we basically just extracted or just transformed those pixels, raster pixels, into vector polygons, which are going to be useful for us to understand when we make some plots here. That's why we're transforming from raster to vector. Now, the next step is so if I just print the object pixels, we still have all of those polygons inside of each one of these cells. I want to basically open that up. I want to bring those 3,600 some rows into the main data set, which is the pixels data set. Right now, the pixels data set has 30 rows. When we bring out these cells under pixel column, we're going to have a lot more rows, right? It's going to be basically 30 rows where each one is for a different date. So 30 times 3,600 something. That's how many we're going to have. Going back to the code, if you add a pipe, we're going to call the function unnest, and we're going to specify we want to unnest or open up this column called pixel. If you do this, and then you just print pixels by itself, maybe that was not a good idea. There's 69,000 rows now because it's the same combination of date and the number of pixels with the gradient DVI in a geometry. All right, so there's a few more things that I want to do here before we keep going. One of them, if you add a pipe, is going to be so what this doesn't have right now is a pixel ID. So let's say we have an image. Within that image, we have about 3,600 pixels, and they're all here, but they don't have an ID necessarily. So I could come here and do like, let me show you. I could come here and do a mutate where I say pix ID. I want to call this pix ID equals to 1 colon and then the length of one of the columns, let's say G and DVI. I could come and do this. If you run that and you print it, well, I think we're not going to be able to see as we print only. What is the issue here? But we have a pix ID, right? That it should go from 1 to 3,500 something for the first date, and then reset 1 through 3,600 something, and then reset for each date. If we look here, I don't think we're going to be able to get to the 3,000 so we can actually see it. But right now, well, let me get the tails of pixels. Maybe that's going to help. If it had worked as I intended on the tail, we would have a pix ID of 3,600 something. But instead, we have the number of rows of the whole data frame, meaning that the pixel ID is not resetting at 1 for each new image. It is just starting from the first image and ending on the last image without resetting. I don't want that. I want that the pixel number 1 on each image to have to have a 1, right? So we should have 30 number 1s here, 1 for each one of the images. Because we don't have that, is not happening right now, we can fix that by doing a group by date right before doing the pix ID. So if we do a group by date before the mutate of the pix ID, now it should work. So now if we get the tail here, we should see the pix ID being the 3,568 as the last one. So by grouping by first and then doing the PixID, it is resetting the PixID every time. All right. The next thing I want to do here is to ungroup. So this is being grouped. I want to ungroup. Then we also need to apply again the function st_s_sf. And then finally, I just want to keep some columns here. So let's do a dplyr select. I just want to keep date, PixID, green and DVI, and the geometry. That should be all for this. So if you run all this again and you just print pixels right now, we do not have any nested columns anymore. We remove them. We have dates, PixID, green DVI, and the geometry. And you see PixID starting as 1 for this image here, and then it resets to 1 again when it gets to the next state. So that's what we wanted. All right. So with this, we are ready to make some plots. So there are 2 plots that I want to do here, but I think before we do that, I want to give you a break because we're getting towards the end here, but we're going to have to do some coding to get these plots going. So I do want to give you all a break, and then when we come back, we'll continue working here to make some maps and also exploring the crop growth curve of these plots, of these pixels over the growing season. So let me put a timer here. And then we'll come back in 5 minutes.
Dr. Bastos,
Yes.
can you show the pixel chunk ones?
Mhm.
I missed. Yeah, that one. Thank you.
Move this out of the way. Yeah. All right. All right, our break is over, so let's return to our work here. Okay, so now we have this data frame that has all the images, all the dates, all the 30 dates with a gradient DVI value for each one of the pixels and their geometry. Now, one thing I want to do here is to create a map. However, I want to create actually 30 maps of this using this object where we're going to have one map for each one of the dates. And I want to use ggplot. So let me ask you for some help. So starting with the object pixels, let's give it a pipe. Now, how would you start this ggplots?
The function map.
Function map.
Hmm.
So well, I guess, can you tell me more about what you're thinking?
I was thinking about using the function map and then using ggplot inside the function map.
Ah, okay. Marco, I like the way you're thinking. We do that. And maybe I think so. I want to take us in a different route, but when I get to the end of that, I want to tell you about if we had gone this route, what would have been different. So
Okay.
let's go the one route and then we'll talk about this. But this is a completely valid solution as well. So I like the way you're thinking, and we could totally do that. It would work the same way, and it would be really the best option in a very specific case that we're going to see when we get to the end of what I'm thinking.
Okay.
Instead of going there, let's go the other route of starting with ggplot. Now, what would you do here? So this is what pixels look like. What function
Should we
would
do a GeoMSF?
Yes, GeoMSF, right, Kathy? Absolutely, because, well, at this point, this is an SF object, right? So we need GeoMSF. So I do want to both fill in color our map, but truly maps according to one variable in our data frame. So what would that be? What do you think, Mohit? If you said something, I didn't hear. So we want to make a map, right? So what do we want our polygons, which used to be pixels, to be colored by?
G and DVI.
In DVI, right? So we want our fill to be equals to G and DVI, also our color to be equals to G and DVI. And then, well, so there's going to be a few things that we will have to do to just make it look a little bit nicer. But if I just run this now, let's see what happens. Okay, so we got our field back. And maybe you cannot tell, but what happened here is we basically have 30 images on top of each other right now. What is needed here to fix that?
Facet grid.
Yes, to use a facet, right? So we can use grid or wrap. I would choose rep in this case. And what is the variable that you would specify, Marco? Let me bring it.
Date,
Can you say that again?
date.
Date, right? That is the column that we want to specify. So if you go ahead and run this, takes a moment here just because there's a lot of data, but this is what we end up with. Even though now it's still looking weird, we're gonna make it look better, but notice that we have a plot for each one of the dates, right? That's basically what we wanted to have. Now, a few things that we're gonna do here to make this look better. So one of them is I want to change the theme map, because then it's going to remove all the long and lat from the y, x and y axis. So theme map. All right, so it looks a little bit nicer. I want to shift. So right now our legend is on top of the plot. I want to shift it to the bottom. So if we go back to the code after the theme map, we're going to use the theme function. And I don't know if you recall, but we used this a few times. There's an argument here for legend underscore position. We want to say bottom. All right. The next thing is I want to change our scale color and scale fill, because we're changing both here on the AS to something that is color blind friendly. So as you probably already know where I'm going with this, we're going to use scale, fill, Verities C. And again, because we're changing both fill and color inside of the AS, we also want to apply scale color Verities C. So this is how that will look like for us. Okay, I think that's probably enough for now. So for us to better visualize this, I want to export this to file. So I already left you here the code. Just run that. Did you save? And once that's done, if you navigate to files, go to the output. Now there is an object called time series. If you just open that, this is what you would see. All right, Marco, getting back to your point before of using the map function to do a ggplot for each one of the dates instead of using facets. If we would have done that, and there are cases that we do want to do that. And let me take one step back and tell when you want to do that instead of this. So instead of doing the map function, we use the facet function in ggplot, which gave us all the 30 plots that we're seeing right in front of us. And notice that by doing that, by using the facet function, we only get one color scale, right? So we get one GNDVI color scale that basically takes into account all the lowest values from whatever image, all the way to the highest values from whatever image, right? It takes the entire range of data for all dates to create the color scale. This is a good option when you do want to see the progress of the crop over the growing season. So we see that low green DVI values happen in early May, where probably when was either bare soil or maybe it was really close to planting, where the crop was not quite there yet. And as the time progresses, you start seeing that on the green DVI scale, it starts to become lighter green and then yellow, which is the highest green DVI. We see the highest at least of the images we have here, it looks like the highest gradient DVI happened around, mid-August. That's where it seems like it peaked. And after that point, even though we don't really have many great images, complete images after that point. Maybe in September 24th is a good one. But we see that September 24th, almost a month over the peak, it's already decreasing, right? It's already lowering the gradient DVI at that point. And we just see that pattern continuing all the way to November 26th when it becomes really low gradient DVI, really dark blue in this case. So taking a step back here to tell you that if you use the facet, it will create just one color scale for all images. That is great when you're trying to see the progression of the crop like we can see here. However, as you would imagine, if I would have had a color scale individually for each one of these plots in a way that that color scale would have minimum and maximum just for that date, you would be able to see the variability within a date a lot better, right? So imagine that if we were to pull just this 0502 image and just plot that, the color scale would basically accommodate the minimum and maximum just of that date, and therefore we would be able to see more variability in color. Of course, the data behind it is still the same. It's just that the visualization in color would be a lot better if each one of these plots had their own color scale and range. If that would have been the goal here, if we wanted to have created 30 plots where each one of them had their own individual, separate, independent color scale, we would have done what you said. We would have done the map with a ggplot and not use the map, or sorry, not use the facet function, but use the map function instead. Does that make sense?
Yes.
Was everyone else able to follow what we're talking, what I'm saying here? And we're not gonna do that here, just for sake of time, but I've done both ways in the past, and those were the cases where I use one or the other. All right. So, well, okay, let's just a few things to notice from this plot. So again, we see that for many dates, we have only partial coverage. That's because that those pixels that are missing, they were classified as clouds, and therefore they were removed from the image. Another thing interesting to notice here of some of the patterns, well, again, we see the evolution of the crop, right? So we see that early May was really low gradient DVI. It peaks around mid-August and then starts to decrease after that point until it's harvested. We don't know exactly when this was planted or harvested, but this is also one application that you could have. We are not doing that here, but imagine that you could use a time series of satellite imagery to estimate planting and harvest dates. If you're working with a grower, let's say, or maybe working with data from a grower that you don't have contact to the grower anymore because the work happened many years ago, but you have imagery, you have the field boundary to pull imagery, and you need planting date and harvest dates. You could get a pretty good estimation of those things by looking into satellite imagery. There are whole papers that look into that very specific use case. So this is very useful for that as well. Something else that I found interesting about this field here. So we see, it's too bad we don't have this image complete, but we have, so October 29 and then November 3rd. What do you think is going on there when we compare both of those?
I think the field was harvested.
Yeah, right. I mean, that's my guess as well. I'm guessing that we were kind of lucky enough to get the transition between harvest, like the grower probably started harvesting on one side and stopped, or maybe was just not able to finish in one day, and then it was going to continue the next day, and then we can really see that transition between what had been harvested and what was still to be harvested. So that's pretty cool to be able to tell that just from satellite imagery. So in this case, most likely harvest happened at the end of October. All right. Okay, so the next thing here is I want to show you. So here's what I want to do. I want to have a plot where I can take, so let's say if we were to go back to this time series and I wanted to say, I don't know, pick one pixel here. I want to take one of these pixels, whichever one we're talking about, any one of these pixels. I want to pick that pixel and basically keep track of gradient DVI for that pixel. So we would focus on one pixel and extract the gradient DVI value of that pixel across all the images and make a plot of it with date or time on the x-axis and then pixel level gradient DVI on the y-axis. And you would see something like starting low, going up, and then getting low again at the end of the season. That's what I want to do next, is for us to take a look at some of these pixels and their behavior over the growing season. That's my goal with the next chunk. So if you come here, let's plug that right into ggplot. So again, the same object that is called pixels. All right, let me ask for help from some other people. Benedetta, what would you put on the AES here?
You put GNDVI.
What would be GNDVI?
Filo equal GNDVI.
Sorry, I'm missing the first part of what you're saying. Just say y-axis or something like that.
No, I was actually saying feel equal NDVI, but
Oh, feel. Okay, gotcha. Sorry. So, well, let me ask this. What do you think should go on the y-axis? Maybe let me start there. Okay, can someone help Benedetta? Luke, what do you think?
Do you mean you want to do G and DVI on the Y and then yeah, and then I guess that would be date.
Dates, right? Yes, and sorry, and maybe I didn't communicate like in enough detail to help you out see the vision, but so just saying again, like in simpler terms, I just want to see the progression of gradient DVI over time for a pixel. So this is definitely what we want to do. Gradient DVI on the y-axis and then date on the x-axis. All right, so before we run this, we're gonna add a geom. We could add a geom point, but I really want to add a geom line, which is just a geom point connected with the points connected, right? And I do want to change two things here. One is, well, you know what? Let's just go ahead and run this, and then I can show you, we can kind of edit on the go. All right, so if you run this, you see this mess. What is going on here is that geom point, or I'm sorry, geom line is basically connecting all the points inside of a date and then making a connection to other dates. To avoid this from happening, we can come back here on the AES. There is an argument we have not used a lot, but it's called group. So we need to say what is the column that has the grouping that we want, that points within that group to be connected. This here would be pix ID. So the ID of the pixel is what we want here. We run this. Now we have 3,560 some lines where each line represents a pixel. But it's really tough to understand what's going on here. It's not very useful. So one thing I want to do is, before we get into ggplot, let's go ahead and just filter some pixels. So we don't show all of them because they're all overlapping. So let's do a filter. I want to filter pix ID, which is where we have the pixel values. Oops, not an equal sign, sorry. Actually going to be a percent in percent. I want to filter some pixels, but I want that to be random. So I could come here and say pix ID in 1 through 10, for example. We could do that, right? And if we do it, you go ahead, it's going to show you the response of the first 10 pixels, which is okay. You know, there's nothing special about those first 10 or other pixels. But if I wanted to get a random set of 10 pixels, I want to show you how we would do it. Instead of giving the C function, we're going to use a function called sample. So the function sample, it works by us giving it a sequence of numbers. So the sequence of numbers is going to be 1 through 3, 5, 6, 8, which is the total number of pixels per image, comma, and how many random numbers we want. Let's say we want 10 random numbers. If I just run this sample of this, it basically gives me 10 random numbers from 1 through 3,568. If we run it again, it's going to be 10 new numbers, and again, 10 new numbers. It's always a random sample. So if we do this instead and run the function, it's going to give us 10 random samples across the image. We don't even know where they're coming from in the image. But the reason why I want it to be random is maybe pixels 1 through 10 are at the border of the field, and therefore they may be similar to each other, but they may not be representing how other pixels in the field behaved. In this case, by pulling 10 random pixels, we have a better chance of exploring the variability across the field because we're using that randomness. We could, and there's nothing special about 10 pixels. It could be 20, right? It could be more, it could be less. The main thing is just that we get a manageable number of pixels that we can easily visualize, and that is random across the field. All right, before we interpret this, a couple of other things I want to show you here. Remember that I told you that one of the reasons why having the date column being a date variable was important was when it came to plotting. As you can tell here on this map, on this plot, the x-axis just has July and October. Where did it get July and October? July and October are not in our data frame. In our pixels, there is no July and October. We have the full date, but we don't have July and October anywhere here as the words. The way that it works is because this column is of type date, R knows how to handle it when it's showing that on an axis. And the default behavior that it used was to show already, or to show by every 3 months, I guess. July. Yeah, every 3 months, I guess. So July and then October. But the fact that it is a date column also gives us a lot of flexibility to ask, how do we want to show it on the x-axis? So after the geom line, add a plus, let's call a function scale underscore x underscore date. So our x scale is of type date. So we can do a lot of different types of breaks and titles or text on our x-axis. I want to call the argument breaks, and I want our breaks to be the exact dates that we got imagery for. So we can clearly see when imagery was collected and the size of the gaps that we have. For that, we're going to call the function unique, and we're going to ask for the unique values within the object pixels, $, column date. If I just run that unique by itself, so kind of like outside of ggplot, it's just a list of all the dates. But now, if you run this within scale x date, it knows exactly where the images happen and is giving you exactly that break on the plot. Almost sneezed, but not this time. Now, another issue here is that we have the full dates, which means that they're all overlapping, which is not useful as well. To fix that, we're going to call the function theme, where it has an argument for axis text dot x that allows us to change a lot of things about the text on the x-axis. Because we want to change the actual text, we call element text function that has an argument for angle. We want angle to be equals to 45. Has an argument for age just, which is the horizontal adjustment or horizontal justification, not adjustment. I want it to be equals to 1. If we use this, now it's going to change the angle and the justification of the dates, and then you can see better like where things happen. So this helps us understand where there are gaps in time, right? So we see there is a huge gap here between May 15 and we had a whole month gap without images between May 15 and June 16. And again, this is because of cloud coverage. And then we had a lot of imagery here between June and July, so about a month of a lot of images, and then we had another gap, and so on. So it can really more easily to see when we had gaps in imagery. Another cool thing is, well, every time you run this code, you're going to get a different set of lines. But overall, we see the same pattern, right? So we see a lower green DVI early in the season. This is probably around planting. And then the crop increases in green and DVI, peaks around August, mid-August, and then starts to senesce until it is harvested. Right? This is a very typical crop response across the growing season, and we can keep track of that by, on the pixel level, by doing a plot like this. All right. Well, any questions about this?
In case we want to keep only the pictures where we have the whole field, is there a way to do that?
That's a great question. Yes. So if we just look here, for example, well, there is an automated way of doing this that I did not include in this script, which is basically calculating the number of NAs in each image. The number of pixels, the number of total pixels is fixed. So you could just calculate the number of NAs, divide that by the total number of pixels, get the percent NAs, and then you can just make a filter where if the percent NA is larger than a given threshold that you give, then remove the image. We can definitely do that. And again, we can do it in a more automated way, but if you prefer to be doing a simpler way, we can just come here and check. Like we could probably drop May 15, we can probably drop, July 9th, and so on. I mean, there's a lot of ones we could drop here. So what you could do as well, if you're doing on a more manual way, you could come to right here on the pixels, you could just do a filter. So we could say date. I mean, you can either filter in or out, right? So if we want to filter in, we would do something like, let me just get some examples here. So let's say if we wanted to filter, well, let's filter out. I think that's going to be easier. So 2017-05-15. So we can come here and say 2017-05-15. And if so this would filter just that image. To flip that, to say I just do not want this one, we give an exclamation point and wrap all that in parentheses. So right now, all images crop has 30 rows for 30 dates. If you do this, well, we still have 30 rows. I'm not sure why. 2017-05-15. Maybe we have to say as date for that to work. Let me try that. Yeah, so we have to use as date. But basically you would do this. So for each date that you would like to drop. So let's say let's try a few more just to show this example. Maybe we want to drop 0709. Maybe 0823. 0912 and 19. 09. And maybe 1014. Maybe let's do that one more. All right, so I just ran that. I mean, if you're not following, that's all right. This is just an example for us to see how they will look like. But now if you rerun the map here, and then we save it. We would see that now the time series does not have those images, right? So there, we can definitely do that filtering, and that's probably a good idea, Marco, is to to keep images that have a higher quality, data quality as well. Maybe we could even remove some others here, but just for an example, providing an example, I think that was sufficient. And of course, if you then run again the next plot, that's also going to be impacted. So we have less dates here now. Awesome. Any other questions? All right, so I just want to tell you what's coming next. So next week, I want to give you the final project, which is basically going to involve everything that we've done this semester, but applying those skills to a new data set. I was actually, so in previous semesters, I was using data from a farm that some of my colleagues have collected in the past, but I don't have a connection to the grower necessarily. It is a grower in Georgia, but I don't know him myself. This year, I was able to get data from a grower that I work with, and he has a lot of really great data and a lot of it similar data to what we've been using in this class. So my goal then is to give you a data set from his farm in a way that whatever you do, I will share with him. So he gets something back as well, right? So he shared his data with us, and he is interested to see what we can understand of his field as far as the variability, whether or not his fields would be good candidates for variable rate, and some other things that we're going to do next week as well. So I'm really excited because it's the first time that I have data from a grower that I have a relationship with, that I can really go back to that grower and say, hey, this is the amazing things my students found in my class. Check this out. Check if any of this makes sense to you or helps you in any way. So that's going to be next week. Also next week, the next step of this lecture is going to be the following. I think we talked about this before, but for this field here, we have yield data for 3 years. We just pulled imagery for one of those years. I'm going to have an assignment for you to do the same thing that we did here, but for the other 2 years. And once we have that, then we're going to do a spatial temporal stability classification. However, not based on yield, but based on imagery. My task for you then is going to be, can we predict spatial temporal stability classes in a field if we do not have yield monitored data and just use remote sensing for that? There are ways we can do it, and that's going to be the next exercise, is to basically create spatial temporal stability classes only using remote sensing. And in our case, because we also do have those classes from yield data, to compare and see how are they related to each other. So that's what's going to come next Tuesday, and also introducing the final project. All right, I think that's all I had for you today. Anyone has any questions before we wrap up? All right, so I'm going to create an issue for attendance. Make sure that you respond to it. All right, so the issue is open. Claim your attendance, and if you don't have any questions, then you're dismissed. And otherwise, I'll stick around for a few more minutes to answer any questions. And if nothing else, I'll see you next Tuesday.